You think you found a planet, but is it really a planet? And so, right.
Thank you. Yes, so my name's Tom, as you heard. I'm from Cornell, the Center for Astrophysics and Planetary Science, and I'm also affiliated with the Carl Sagan Institute for Habitable Worlds at Cornell. And as a result, I'm contractually obligated to quote Carl Sagan at the beginning of every talk. So not really, but I do like this quote. This is from one of Carl's later books. He said, "Science is more than a body of knowledge, it's a way of thinking. The method of science, as stodgy and grumpy as it may seem, is far more important than the findings of science." Maybe that's a little bit of an exaggeration, but I like it that Carl was really invested in scientific methodology, and I think he would approve that one of the concerns of this week's school in his name is to talk a bit about scientific method, not just the results of science. And that will be the topic of my talk today. Some of the statistical methods, the principles underneath how you go about quantifying the strength of evidence of a planet. So by way of motivation, let's talk about weather. Where I'm from in Ithaca, weather's a common topic of conversation. Let's imagine a kind of idealized weather predictor that just predicts rain or sun. And here's a table of that forecaster's predictions and joint frequencies of the prediction and the actual weather. So a quarter of the time predicts rain and it does rain. A quarter of the time predicts sun and it does sun. It is sunny. So, and then half the time predicts rain, but it's actually sunny. So not the greatest forecaster in the world, but providing some useful information. That's suitable for Ithaca. I suppose in Pasadena, in place of rain, you might have swelter. I mean, rain is probably a desirable outcome here in California these days. So, but I'm going to stick with rain and sun. I am from Ithaca, where it's cloudier than in Washington State. Okay, so here's the weather forecaster, the same table I showed you before. I've added a little bit of information. The marginal frequencies, so listed in the margins are the sums down the rows or across the columns. So 3/4 of the time the forecaster predicts rain, 1/4 of the time predicts sun, 1/4 of the time it's actually rainy, 3/4 of the time it's actually sunny. So the forecaster is right the times, the cases that are marked in blue, the diagonal. If you sum them, that's half the time. Now, some astute observer notes that a prediction of sun every day would be right 75% of the time. And that person applies for the forecaster's job. Should they get the job? After all, they'll be right more often than the actual weather forecaster. Well, with a forecaster, you will never be in an unpredicted rain. There's this interesting zero there. The forecaster is actually using data about the weather and telling you something different based on data. The observer is just flipping a biased coin, or actually not even flipping a coin, just always saying sun, not using any information. You'll be in an unpredicted rain 1 day out of 4 with that observer. So this is just a kind of simple toy problem. I haven't given it enough structure for it to even be a real statistics problem, but it does offer some interesting lessons. This is from a paper, a very old paper by James that I encountered when I was stumbled upon when I was a graduate student in the 80s. And it has much more structured examples in it than this one, but it's a very beautiful discussion of these kinds of ideas. And the point of this little exercise is that the value of an inference, an attempt to reason in the face of uncertainty, more often than not, I would say, lies in its usefulness in the case at hand. Long-run performance, the observer doing better in the long run than the predictor, is not an adequate criterion for assessing the usefulness of a particular inference in the particular case at hand. If you're interested in long-run performance, if you're going to be betting on the weather prediction, then you need to compute the long-run average of the performance of predictions, but that's a separate thing from how you should measure the performance of a prediction case by case. So why am I bringing this distinction between single case and long run performance up? It has to do with how you go about answering statistical questions. And the types of questions that I want to talk about today, motivated by our topic of the whole workshop, are planet detection questions. And in two different types. First, for a single host, observing a single host, asking the question, is there a planet orbiting this observed star? A more complicated version, which we won't talk about, is how many planets are orbiting this star. So you're choosing between, instead of rain and sun, you're choosing between no planet and one planet, or more generally, 2 planets, 3 planets, and so on. Also, I will briefly talk about at the end planet demographics. Imagine looking at a population of host stars in a survey. How many of these n observed stars host a planet? Or what is the planet multiplicity distribution if you're talking about more than one planet? That's a different type of question, but it's concerning detection across an ensemble. And you could even, instead of just talking about the particular sample you observed, you could also try to extend it to the whole, including the unobserved population and accounting for selection effects and things like that. So one of the things that I hope you'll take away is that these two questions are inextricably related. You actually can't provide a good answer to this one without doing this one. But to do this one, you actually have to do some of this. And there's this kind of feedback loop that happens. There's a way to handle that, and I'll only have 1 or 2 slides on that. Just have limited time. So why that weather forecaster discussion? It's because there are 2 styles, if you will, of statistical approaches for how to answer these kinds of questions. Both of them use probabilities to quantify uncertainty about a detection. But they have they're based on different understandings about what probability, what that word means. And those different understandings lead to different ways to use it, different actual numerical calculations. There's the so-called frequentist approach, where probabilities refer to how often a procedure will be right in the long run. Like if I calculate a 68% confidence level for something, that's a procedure that if I apply it to many hypothetical data sets taken in similar circumstances, I should get the real value of the parameter in the interval some desired percentage of the time. Then there's the historically older but kind of resurging approach called the Bayesian approach. And in here, probability is a more abstract kind of thing. It's a measure of strength of evidence for or against rival hypotheses, explaining the one case at hand. More abstract, but with theory that shows it's related to long-run performance, sometimes in a non-trivial way, sometimes in a straightforward way. All right, so depending on which of these approaches you adopt, you end up using different methods to address these 2 types of planet detection questions. So this slide kind of represents our agenda for my talk. It will reappear at the end, and hopefully by the end you'll have some beginning of understanding of what all the bullets are. So for single host planet detection, from the frequentist point of view, you would address that with what's called null hypothesis significance testing, typically using a maximum likelihood ratio. So these terms will hopefully, if you haven't seen them already, they'll be explained in the talk. And there are kind of 2 rival approaches for how to do this. One that adopts a fixed a priori threshold and just says whether you pass or fail, and one that reports kind of what would the threshold be at which you might have detected it in this system. That's called a p-value. It turns out that this approach reports false alarm probabilities. This approach, astronomers often report as giving you a false alarm probability, but it doesn't. And hopefully that will become clear. From the Bayesian point of view, you calculate something called the posterior probability for an odds. And whereas the frequentist approach typically looks at the maximum likelihood, the most probable model that predicts your data, the Bayesian approach looks at what's called the marginal likelihood, doing an average, or a sum, like we did in that table, the margins of that table. It kind of averages over the possible models, possible parameter values that might describe your planet to account for uncertainty. Well, there'll only be maybe 2 slides on planet demographics if I survive in terms of time long enough. But I do want you to see that there are techniques. Well, I'll only present one of them in 2 slides, hierarchical Bayesian modeling. From the frequentist approach, there's also an adaptive thresholding approach where you look at your distribution of p-values among all the candidates you have and use that to select a p-value threshold. I won't talk about that. That would be interesting too, but there's just not enough time. And then hopefully you'll see that there's this feedback loop between these 2 approaches. So that's our agenda. It's a lot to talk about. I was given a list of things they wanted me to cover, and that includes these things. It's kind of impossible to do it justice in an hour. I don't have 60 slides. I threw a bunch at the end in case questions come up, but I do probably have more slides than I can handle. That said, if you're stumbling with something, please raise your hand or just shout out and ask a question. I will be here at least through Thursday morning. So even if you have a small question, no question really is small. I'd like you to understand it. I stayed here so I could talk to people also and learn from you all. So please, mark down even your smallest question and come talk to me sometime. That said, I will probably be doing some real-time editing. Okay, so here's our plan. So planet detection is comparing a model with a planet to one without it. But before we talk about that, model assessment, I want to talk about parameter estimation because I think more people have familiarity with things like confidence intervals for confidence regions for parameters. And I want to give you some understanding of the difference between some of these ideas in that setting. And then we'll talk about model assessment. And then just a couple slides, hopefully we'll get to the demographic connection. All right, so parameter estimation from a frequentist and a Bayesian point of view. As I said, the 2 approaches have different ways of interpreting what you mean by a probability. Let's talk about it in terms of probability densities or probability density functions, PDF. Hopefully, I'm assuming you've all seen probability distributions, density functions, cumulative distribution. But from a Bayesian and a frequentist point of view, you think of them in different ways. From a frequentist point of view, probabilities always describe variability in outcomes from repeated trials, doing an observation different times and getting maybe looking at the same signal but with different noise, or sampling from a distribution repeated times. A probability density describes how the values of X, whatever it's a function of, how they would be distributed among infinitely many replications. So here's a PDF, it's a continuous function. It describes basically the limiting histogram of the values of X that would arise, right? From a Bayesian point of view, probability is meant to quantify, to describe the uncertainty that you have about what the value of X might be in the one case at hand. So P of X doesn't describe how X is distributed, but rather how P is distributed. You could think of it as like a density in classical mechanics, like smooth matter density. It's the matter that's distributed as a function of X. Similarly, with a Bayesian PDF, it's P that's distributed. X has some unique value. The mass of a planet has some unique mass. If I repeatedly observe that system, that mass would always be the same. I might get different noise in my observations each time. But as a result, from the frequentist point of view, you could never talk about the probability for the mass of a planet, because that mass is not distributed in a non-trivial way. But from a Bayesian point of view, you could talk about your probability distribution for the mass of the planet. You're saying the mass has one value. I don't know what it is, so I'm spreading my probability for where it might be out on the axis. All right, so that sounds like a kind of rather philosophical distinction, but it actually has profound practical implications. If you're adopting the Bayesian or frequentist point of view, you will write a very different computer code to do your calculations, and hopefully you'll get some sense of that. So Brad Efron, a very famous, one of the leading statisticians in the world. You might have heard of him. He's the inventor of the bootstrap and many other clever ideas in statistics. He was the president of the ASA, the American Statistical Association, in 2005, and gave a talk on, basically the idea of the talk was that in the 21st century, statisticians need to try to be bringing Bayesian and frequentist ideas together in some kind of yet to be developed synthesis. But, one of the statements in his talk was that the 250-year debate between Bayesian and frequentists is unusual among philosophical arguments and actually having important practical consequences. So I just want you to know it's not just some renegade astronomer telling you that these are interesting distinctions to make, but one of the most admired statisticians in the world and the ASA president has made the point repeatedly in his writings that these two things tell you to do different things. We really got to sort out what to do with those two approaches. So let me give you one example of how the different ways they use one piece of probability theory, and that's Bayes' theorem. So Bayes' theorem as a mathematical result is not controversial, and it's rather trivial. So it comes from looking at a joint probability and factoring it two ways. So the probability that A is true and B is true can be factored as the probability of A times the probability of B given A, or the probability of B times the probability of A given B. So set these two right-hand sides together and solve for this one. So this one is equal to this product here divided by this. So that's Bayes' theorem. Now, from a frequentist point of view, if all of these probabilities have to be histograms of things that would be different every time you repeat a trial or experiment, then it's only valid when A and B refer to events. That's a technical term in statistics. It's a statement about the same underlying random outcome, where in the frequentist point of view, random means you'll get a different result each time you repeat. So only when the probabilities describe variability are you allowed to use this theorem. Here's a trivial example. Suppose that A is I, the number of dots that would show up on a fairly rolled die, and suppose B is the event that I is a prime number. I is in the prime, so the number of dots is a prime number, 2, 3, or 5. So then here's Bayes' theorem, P of I, given that I is prime. So there's a prior for I, that's 1/6, the prior for getting a roll of a die. There's this thing here called the sampling distribution. So the probability that I is in the primes, I use this kind of double bracket notation to be an indicator. That's something that's 1 if the thing inside is true and 0 otherwise. So if I happens to be a prime, this is just 1, right? This is the P of the probability of being a prime if you know I, right? So if I know I, it either is or is not a prime. So it's 1 or 0. And then the set of primes that among the numbers 1 to 6 are these 3. So the probability of it being a prime is 1/2. So here's Bayes' theorem. It just tells you that the probability of getting 1, 2, 3 up to 6 is 1/3 if it's 2, 3, or 5, or else 0 if you're insisting on it being a prime. All right, trivial, but I just wanted you to see that you can use Bayes' theorem to do frequentist calculations, and it is important. From a Bayesian point of view, Bayes' theorem is potentially valid for any propositions referring to anything, so long as we can assign all the probabilities that are needed in Bayes' theorem and interpret it as strength of an argument from whatever is in favor of whatever it is we're making a statement about. So in particular, let's let B be a statement that tells you what the data are, D, and let A be a choice of an assertion that one of among a set of rival hypotheses explain the data. So H sub I, or I indexes some set of rival hypotheses. Then Bayes' theorem can take this form. So this was A and B before. So P of hypothesis given data is P of hypothesis, P of data given hypothesis divided by P of data. So when the symbols have these interpretations, data and hypothesis, these terms in Bayes' theorem have a special name. This thing on the left is called the posterior probability for H. This is called the prior. this is a probability for D, but as a function of H, it's called the likelihood. Never use the term likelihood for the data. Likelihood is a term created to distinguish the probability for the data, this thing as a function of the data, from its dependence on the thing to the right of the bar, the likelihood for the hypothesis. So if you say likelihood for the data, that's like the giveaway that you're not a statistician. I know few of us are, but we want to at least try to become effectively statisticians. And this thing on the bottom is called the marginal likelihood. Only in astronomy and physics sometimes is it called the evidence or the Bayesian evidence or something like that. It's a terrible term, but I guess it's in use. So the evidence is the data. So maybe the weight of evidence was sometimes used for this term historically, but that would be a better term. But, so for an example, let's go back to Laplace. In 1818, around that time, he computed the posterior distribution for the mass of Saturn in units of the solar mass. Here's a phrase, here's a statement. It was probably sounded better in French, but applying to them the data, my formulae of probability. He was the first person to write down Bayes' theorem in this form. It wasn't Bayes. He wrote a special case, but it was Laplace. I find it's a bet of 11,000 against 1 that the error of the result is not 1% of its value. So here is Laplace's posterior. He was doing things in a Gaussian approximation. So it was a Gaussian. He found a best estimate for Saturn's mass in solar units. And this is what's called a credible region in modern terminology that is 1% of the most probable value. And that was he chose the 1% and then calculated the probability that's inside of it. These days, the convention is usually to choose an interesting probability like 68% for 1 sigma. And we would have reported something like this, a plus or minus 1 sigma bar. The green bar is the current value. So he would have won that bet. Nice. But so from the frequentist point of view, you're not even allowed to say this statement, right? Mass of Saturn is the same every time you repeat observing it. So you can't talk about a continuous probability density for the mass of Saturn. So one of the reasons I showed you this example, besides it having to do with a planet, is just to point out that the Bayesian approach to using probability to analyze data was actually historically the original one. It fell out of favor beginning in the late 1800s and then started getting back into favor in the mid. All right, so let's start building up some lingo and some structure and talk about inference with what are called parametric models. So what do I mean by that? So I mean that there's a set of models that even in the full theory, it could be a countably infinite set if you want, each with some set of parameters that each specify what's called the sampling distribution. I've already used that term. It's the probability distribution for which you would predict possible sets of data. So you specify a model and its value of the values of its parameters, and then if knowing that you can calculate the probability for the data, then you have a parametric statistical model. If we fix attention to the observed data and look at this thing as a function of the parameters, that thing is called the likelihood function. Again, it's likelihood for the parameters, probability or sampling distribution for the data. We could be uncertain either about the choice of the model, or if we focus attention on one model, about the choice of parameters. In the latter case, you talk about estimating the parameters. In the former case, you talk about comparing the models. Sometimes, so from now on, it's kind of cumbersome to be writing D observed. I will, whenever we're doing a Bayesian calculation, D will always refer to D observed, but in many frequentist calculations, it will be more generally the space of possible hypothetical data. Another bit of lingo, if there are no free parameters in a model, it's called a simple hypothesis. But when there are free parameters, it's called a compound or composite hypothesis. That is, it's a set of hypotheses. Each theta is a choice of one of that set. So a class of models that is very common in statistics and in exoplanets is we might call additive Gaussian noise models, or a statistician might call these nonlinear regression models with normal errors or normal noise. So here's the setup. The data D collectively are some set of measurements, lowercase d sub I. Those are noisy measurements of some underlying signal, say a function of time, that's specified by some parameters theta, and that's measured at some number of sample points. I'm just going to use this abbreviation. F sub I is the value of that function at the time of the ith sample, but that prediction is a function of the parameters. So the data are some prediction that depends on the parameters. The model is that this additive noise model is that the data are some prediction, parameter-dependent prediction, plus some error, and we're going to say that the error has a normal distribution with some known standard deviations that might differ from measurement to measurement. And I'm going to assume here they're independent. In the next talk, you'll hear about dependent noise and other things like that. So we seek to learn theta for a given model or to compare different models. One thing worth noting, if you ever talk to a statistician, a model refers to everything. Like they would call this, you know, a regression model, a normal regression model. We would call this, you know, like a Keplerian orbit model if these were RVs and this was a Keplerian velocity curve, right? So astronomers tend to use the term model just to talk about the signal. Statisticians use the term model to talk about everything you need to get a probability for the data. So just keep that in mind if you ever read a statistics book or talk to a statistician. So the likelihood, the probability for the data given all that stuff is a product of the normal distributions for the noise, which is the data minus the prediction. So hopefully you're all familiar with a normal distribution. So 1/2 the difference squared divided by the variance, the sigma squared. Products of exponentials, you can sum the exponents, so we get that -1/2 from the Gaussian, and then a sum of the kind of weighted squared differences, and we often in astronomy call that chi-squared. So the likelihood function is e to the minus chi-squared over 2. So if you've never seen likelihood or maximum likelihood before, but you've done chi-squared or weighted least squares, just every time I say likelihood, think, okay, take my chi-squared function, negative it, so flip it over, and then divide by 2 and just exponentiate that thing. So the posterior, you take a prior density, maybe to express ignorance, you might take that to be uniform. That deserves significant discussion. There'll be 1 or 2 slides about it if we get to the demographics. We don't have time for that discussion now, but so there's a prior times this likelihood. That's that top line of Bayes' theorem. It gets divided by something that was the P of data, so it didn't depend on the parameters. That must be a normalization constant, and that thing is what I've called the marginal likelihood. Marginal likelihood because it's the likelihood and doing a weighted sum like we did in that table listing in the margin. Okay, so prior, it's just the numerator in Bayes' theorem integrated so that the whole thing is normalized. So if you have a least squares or a chi-squared code, just as I said, think of chi-squared as -2 the log of likelihood. And then if you want to make statements about theta, you do it by integrating over regions of theta. Or if you want the posterior mean of theta, you multiply this by theta and integrate that. So Bayesian inference amounts to taking your chi-squared, exponentiating the -1/2 of it, and then doing numerical integration. If it's just a few dimensions, you should do that by a quadrature rule like Simpson's rule or the trapezoid rule. In higher dimensions, you do it by Monte Carlo, either IID, independent identically distributed Monte Carlo, or Markov chain Monte Carlo, which we won't talk about. Those are the popular methods for doing this. All right, so now with that background on what a parametric model is, let's talk about confidence regions and their Bayesian counterpart, a credible region. So let's look at like the simplest case of that additive noise setup. So imagine we're estimating the location parameter, the mean of a Gaussian distribution from a set of samples. So it's that noise model where the function is just a mean, a mu, a single scalar parameter mu. I'm going to call the data that I called DI before, I'm going to call them XI here. I should have fixed that, but I didn't have time. And then our goal is to report a region summarizing the uncertainty. I'm focusing here on quantifying uncertainty more so than coming up with a single best in some sense estimate. So here we're going to assume that the noise standard deviation is known. The only free parameter in the problem is mu. So the sampling probability is just that Gaussian distribution. So remember, there was a prediction, the data minus prediction before. I flipped the order here. I could have written mu minus x squared divided by the sigma squared. When I sum those exponents, I just get chi squared over 2, where the prediction is just the mu. So that defines this a likelihood function, L of mu, which is just, you can see it depends on mu through a squared. It'll have squared in linear terms, so it's just a parabola in mu. Chi squared is a parabola that looks like this. The log likelihood flips that over, and then the likelihood itself is the exponential of that. And so it will look like e to the minus something that's quadratic in mu, so it will look Gaussian. So this is a very important distinction. There are two classes of variables in this problem. Mu is the unknown that we're seeking. It defines the parameter space, right? Or a hypothesis space is a more general term for that same idea, something that indexes the hypotheses. A particular set of the data values is a sample. If there are n of them, then the sample space is an n-dimensional space of possible values of the data. And then here are some standard inferences that I'm assuming you've seen before. Let's define the sample mean just by averaging the data. Then there's a standard error, an RMS error is just the noise level divided by root n. There's a 1 sigma confidence interval that's called a 68.3% with a 68.3% confidence level. That's just the mean plus or minus sigma over root n. A 2 sigma interval, so 2 sigma over root n has a 95% roughly confidence level. So hopefully you've all seen that. That's standard frequency. So let's look at a simple example. Suppose the true mu is 5. We don't know that at first. Suppose we do know sigma is 4, and we're looking at samples of size 16. So sigma over root n is 1. So what would the confidence level be associated with this interval? So I've simulated data sets. For this simulated data set, the unknown true value is this red line here. And I found an interval that extends from 5.5 plus or minus 2. So what's the confidence level associated with that interval? Anybody here to hazard a guess? So sigma over root n is 1. The size of this interval is 2. So the confidence level of that interval is 79%. That's meant to surprise some of you. I'm hoping at least some of you thought it should have been 95%. So what is going on there? So here I show you two intervals. This bottom interval is the one I just showed you before that I claimed was a 79% interval. This top one here, which also is 5.49 plus or minus 2.0, is a 95% interval. So what's going on there? So the green interval uses this rule, the rule that I reminded you of 2 slides ago. Calculate the mean and add plus or minus 2 sigma over root n to it. The blue interval I found with a different rule. I order the data and then I just report the 6th sample in from the left and the 6th sample in from the right. It turns out if you do that, 79% of the time, the true value will lie in that interval. And the trick I played on you is I simulated lots of data sets until I got one where the intervals were the same to two decimal places. In general, they're not the same as I'll show you on the next slide. But the point of this example is that the confidence level, the frequentist probability that summarizes uncertainty, is it's a property of the procedure, not of the particular interval you get for the particular data set that you have. So here are a bunch of simulated data sets with true value of mu of 5, and they're green intervals. That's the standard 2 sigma over root n, and then this new order statistic interval that I just invented as a hack. You can see the green intervals are always the same size, are always the sigma over root n, and they cover the truth more often than the blue interval, which changes its size depending on the data. So the point is that the probability is a property of the procedure. The probability, the number that's associated with the interval you report, made no use of the observed data in its calculations. It comes from doing a simulation like this. What about from a Bayesian point of view, how would you treat this problem? So we already wrote down the likelihood function, right? We said it's e to the minus chi squared over 2 here. You can complete the squared and explicitly write this thing out as a Gaussian in mu. It turns out it's centered at x bar and it has a width sigma over root n. With a flat prior, the posterior itself will be a normal distribution centered at x bar with a width. By convention, you usually show the variance in the normal distribution width. So the width is sigma over root n. So what's called the highest posterior density credible region, the smallest region that encloses a particularly specified probability, that would be plus or minus sigma over root n around x bar for 68% or 2 sigma over root n for 95%. So no consideration of any hypothetical data involved here, but the observed data play a crucial role. They determine x bar. Right? I think I'm going to skip these 2 slides in the interest of time. So some takeaways from this discussion of parameter estimation. The frequentist and Bayesian approaches do very different kinds of summing or averaging. You can do these sums and averages by brute force, analytically, or by Monte Carlo. In the frequentist case, you sum or average over the space of hypothetical data. You calibrate a confidence region by simulating lots of data and seeing how often your rule is right. From a Bayesian point of view, you never consider hypothetical data. You never simulate other data sets. You look at the likelihood function given your one data set and you normalize it with some weighting and you integrate in the parameter space instead of the sample space. So very different types of summing and averaging. As a result, a Bayesian code and a frequentist code may look alike at the likelihood function level, but then what they do with the likelihood function is totally different. Okay. The observed data play very different roles. Frequentist probabilities do not, in fact, they must not, as a matter of principle, ever use the observed data in their computation. The calibrations of confidence regions are done by using simulated data and seeing how often the procedure is right. Frequentist probabilities are always procedure properties. Bayesian probabilities use only the observed data. They're properties of the particular data set you have. Okay. For the normal case we just did, they both produce the same reported estimates and uncertainties that kind of have visually look the same. But that was just a numerical coincidence. It's unique to things like the normal distribution, things in the so-called exponential family. It won't hold in general. All right, so now let's talk about model assessment. So that was what I was hoping to do there was to, I think people are more comfortable with confidence regions. And I think a lot of us, this is certainly true for me when I started delving into statistics, I thought I knew what a confidence region was until I actually went through how they're derived and what their properties are. And it's actually a much more subtle and indirect concept than I realized. So maybe some of you have kind of realized that maybe you didn't understand exactly what a confidence region is. And maybe you were thinking that a confidence region was what a credible region is. But the two things are different. They're computed differently. They mean something different. Now let's kind of do make those same kind of distinctions, but now in the space of comparing rival parametric models. So let's first talk about doing this from a frequentist point of view. And it turns out there's kind of 2 different approaches that people adopt. There's the theoretically right approach, which I'll tell you about on this slide and the next slide. And then there's a kind of not really frequentist approach, which is what everybody uses, not just in astronomy, but not rigorously frequentist approach. That's guided by an intuitive sense that there's something missing from the rigorous frequentist approach, as you'll see. So here's the rigorous frequentist approach. It's called so the common term for all of these approaches is called null hypothesis significance testing. The idea is you pick one of the hypotheses to play a special role, that if you reject it, that will be interesting. That's the null hypothesis. and then you're going to explore how to quantify uncertainty in your choice to reject or accept the null. So you're going to specify, in this setting here where the theory is clean, we're going to look at only a simple null hypothesis, no free parameters, such that rejecting it implies something interesting is present. Somehow we will devise a statistic, a function of the data that measures departure of the data from the predictions of the null model. In the next slide, we'll see that likelihoods are good for doing that, or at least we'll state that. Now, divide the sample space into probable and improbable parts, data sets that would be very surprising under the null and data sets that are more or less typical under the null. And do that according to values of this statistic. So do it, and we're going to introduce this symbol alpha, called the test size or the type 1 error rate, so that the probability of the surprising part of the data space given the null is some small number alpha with alpha specified a priori, like maybe the typical value that Fisher used was that Neyman and Pearson and others used was 5%. So suppose here's the situation. So you have a value of S that separates into a piece of the space that maybe has 5% of probability, with larger S meaning more surprising under the null. So these are kind of not good data sets if you want to believe in the null, right? Devise a threshold so that there's some target probability there, like 5%. That's this pinkish area. Get some data and see where its statistic lies along this line. If it lies in this region, then this is what you're allowed to report. You report that the null was rejected with a procedure that has a false alarm probability or false alarm frequency, if you want to be very specific, alpha, so that this tail area is alpha. So the meaning there is if I adopt this procedure and repeat the experiment many times, if the null actually is operating, then I will be correct. The statement will be correct 1 minus alpha % of the time. So they were guided by this idea that that came up under when we talked about confidence regions, that when you repeat something, your frequentist summary of uncertainty should describe what actually happens in the long run when you apply your procedure over and over. So confidence region does that. Neyman and Pearson insisted that you should also specify an alternative to the null and also compute the error rate for falsely rejecting that alternative. That's called the type 2 error, or falsely accepting the null. For simple null and alternative hypotheses, they proved an important theorem. It's actually called the lemma, the Neyman-Pearson lemma, that the optimal statistic to use is just the likelihood ratio, the ratio of the probabilities that the two hypotheses would predict the data. For composite hypotheses, there's no theorem on optimality that's general, but the popular choice is to maximize your likelihoods over any free parameters. May not be optimal, but it's intuitively appealing. Now, Fisher and others felt that reporting a rejection frequency of alpha, maybe I chose alpha to be 5%, but maybe, oops, could use this, I suppose. But maybe my data lied far out along this axis. It seems like the data are more strongly arguing against the null than just at that 5% level. So that's Fisher's intuition. So he advocated reporting what he just called P, and what today is called the P value, the probability that the statistic would take a value, this should be greater than or equal, but it doesn't really matter for continuous case, greater than or equal to the observed value. So instead of reporting that pre-specified tail error rate, alpha, you report the tail area above the observed value of the statistic. So with what you just learned about frequentist confidence intervals, this should start raising a red flag. That red thing there should raise a red flag. Rigorous frequentist probabilities can never use the observed data when you compute them. In some really fundamental sense, you've probably heard about prior probabilities being important in Bayesian inference. Well, in frequentist inference, all there are prior probabilities. you can never use the actual data you have to compute a probability. So this thing actually doesn't have any simple frequentist interpretation. Fisher just called it P. Astronomers have called this the significance level or the false alarm probability. Statisticians don't call it either of those things, and there's a good reason for that. Many other areas started using that kind of terminology too, and it led to a number of kind of bad results being declared good results, to the point where 2 years ago, the ASA issued a statement on statistical significance and p-values, saying that p-values don't measure the probability that the study hypothesis is true or the probability that the data were produced by random chance. Scientific conclusions and policy decisions shouldn't solely be based on p-values passing a threshold, and by itself, a p-value doesn't provide a good measure of evidence regarding a model or a hypothesis. And they said many other things, but those are some highlights. So I like to call this the false alarm probability fallacy, the way that we as a community have been using p-values, especially in the last 20 years. That's when I first really started noticing it, a little after 2000. So these are quotes, some of them from abstracts of papers on exoplanets. So the false alarm probability for this signal is rather high at a few percent. This signal has a false alarm probability of less than 4%, blah, blah, blah. This detection has a signal to noise ratio of 4.1 with an upper limit on the false alarm probability of 1%. We find a false alarm probability of less than 10 to the minus 4 that the oscillations are spurious. Right? All of those statements incorrectly describe the weight of evidence for a planet in those data and almost certainly greatly exaggerate the weight of the evidence. What's wrong with those kinds of statements? So when you say this signal with a particular value of some test statistic has a false alarm probability of P, remember the number you're reporting, P, is the size of some set of hypothetical data for which the observed statistic was worse than, for which the possible values of the statistic were worse than the observed value, given the null. So there's two things wrong with this kind of a statement. The first is that you've calculated this probability given the null. That is, P is computed assuming that the null is always operating. Like if you're doing a Monte Carlo calculation to calculate the p-value, in that Monte Carlo calculation, there's never a planet, right? So every alarm is false in the world in which this calculation is done. That is, FAP equals 1. The false alarm probability is 1 in the world of this calculation, right? There could only be a false alarm probability that's non-trivial if sometimes the null is not operating. The second thing that's wrong with it is that this is a probability for data that are almost all worse than the observed data. So that p-value refers not specifically to your observed data set, but to a set of data that's mostly including more extreme data. Your observed data bound that set on the weakest side of evidence against the null. Right? So here's what a p-value really means. So I don't know if you know who Don LaFontaine is, famous movie trailer announcer, or Lake Bell. Have any of you seen her movie In a World? So In a World. That kind of thing. So this is what a p-value means. In a world with absolutely no exoplanets, with a threshold set so we wrongly claim to detect planets 100% of the time, this data would wrongly be considered a detection, and it would be the data with the weakest evidence for a planet in that world. That's a mouthful. It's not clear how it directly answers the question, well, is there a planet or not? That's why statisticians give this thing this very ambiguous name p-value. That's meant to mean this, and also meant to kind of hide that it's only a very indirect way to address your question. The one intuitive property of a p-value is that under the null, the fraction of time that p is greater than some number x is just that number x, right? So the fraction of time that p is less than 1% is 1% of the time. The fraction of time that it's greater than 5% is 95% of the time. So you could think of it as just a mapping from S to some new statistic that has a uniform distribution. Okay, that's the It's a surprise ordered relabeling of the data that has a uniform distribution if there's no planet. But surprise isn't enough. The rarity of data, how surprising it is evidence against the null only if there are plausible alternatives that make the data less surprising than it were under the null, that predict the data better. So to do that, to try to do this kind of comparison against alternatives, you have to expand the world of that p-value calculation. I'm not going to go through exactly how that's done. I've run out of time. But there's a way to do it. Instead of computing that tail area, you look at the null, you look at models with a planet, and then you compare the height of their histograms at the observed value instead of looking at the tail areas. That's called a conditional frequentist test. And I have some histograms here that show you that kind of thing, but I'm going to skip those. So you're going to compare the way that two alternatives compute the actually observed value. Now, from a Bayesian point of view, the way you would address this is with what's called posterior odds. You calculate the probability for a model with one planet, the ratio of that probability against the probability of a model with no planets. So each of these you would compute with Bayes' theorem. So they would be a prior times the likelihood divided by a common normalization constant that when you take this ratio drops out. So prior for a planet being present times a likelihood, prior for no planet times its likelihood. This thing doesn't depend on the data. It's called the prior odds. This thing depends on the data. It's called the Bayes factor. And so, in fact, if you try to do that conditional frequentist test that I talked about, in some situations, it amounts to computing or approximating the Bayes factor. You would calculate what's the probability for the observed, seeing the observed value of chi-squared or minimum chi-squared with a planet and without it. You'd look at the heights of those two histograms at the S value for the observed data, not a tail area. All right, so one important new thing Bayes introduces is that when some of the hypotheses are composite, typically if there's a planet there, you don't know its mass a priori or its period or its velocity amplitude. What plays the role of the probability distribution for the data is the marginal likelihood. So these are different curves that have different possible parameter values. You average them, and then you use the curve for the average. That would be the solid blue curve. And then you compare the heights of those two curves with a planet and without a planet. Okay, so the one thing I will say about demographics is that this Bayesian calculation requires a prior probability for there being a planet and a prior probability for there not being a planet. Those are things that are population quantities. It's the prior prevalence for a planet or not. So you need to somehow know those to be able to do this Bayesian calculation. So where do you get those? Well, in practice, you can build these kind of feedback loops. This is a general property of Bayesian inference where you might have different levels of questions. So for example, for RV planet detection, there's spectral data, you model it, you get a radial velocity curves. That actually is a non-trivial statistical calculation. You model those with Keplerian orbits and you do planet detection and measurement. But then you look at data from many planets together and you learn things like the prevalence of planets. That's called doing hierarchical Bayesian analysis. So there's a framework for doing that, which we don't have time to cover, but I only had one slide on it. So that's it. That's the end of the talk. This is that same slide I showed you earlier. So this is the way you answer the exoplanet discovery question, single planet demographic questions. So again, just as a recap, there are frequentist and Bayesian ways to answer both of these questions. The things that I want you to take away are the way that frequentist and Bayesian results use the data differently and do different types of integrals. That one uses maximum likelihoods while the other uses average likelihoods, and especially that you should not be calling p-values false alarm probabilities. And then finally, that there's this important feedback between demographic inference and single case inference. There's no way around that. When you're early in a new field like exoplanets, you just have to either adopt simple interim priors just to describe your present state of uncertainty, or you just explore how your answer would depend on your choice of the prior. And otherwise, you try to look at many systems and build this feedback loop. Okay, that's it. Thanks.
Okay, does anybody have any questions? And there are no stupid questions, and you are supposed to be here to learn, and everybody who's speaking here wants to help you. Yes.
Yes. So that's what you would do.
Could you repeat the question, please?
Yes, oh, thank you. So the question was, when I talked about the confidence interval, the width of the interval was sigma over, I used sigma over root n. Why was it not root n minus 1? And so that would be the right answer if there were lots of data and sigma were unknown. But it's because I considered sigma to be somehow known a priori. That's the difference. So if sigma is unknown and you do that calculation, then you have to somehow worry about the fact that you don't know sigma. If you're going to report just what you know about the mean, the mu, then what you need to do from a Bayesian point of view is integrate sigma. And that changes that Gaussian into something called a t-distribution. It looks like a Gaussian, but it's wider. And that root n minus 1 comes from looking at the width of that distribution. Yeah.
So you just passed the slide. It looks very intriguing. What do you do if you have just one planet?
So you want me to give the slide?
Go ahead.
Okay, so it's an open issue. So there was some discussion of this in the ASA paper. What do you do if p-values aren't so good, even though we've been using them for 70 years, including statisticians? What do you do? Kind of most people actually said to try to do Bayes factors. Not all, but a surprising number of commenters on this ASA statement said that, but it still leaves open this question of what priors do you use. So everybody did, not everybody, but most of the people that commented on this, and certainly me, I think that the p-value is an interesting quantity. It's a measure of how surprising the data are under the null. So it's communicating something. In the Bayesian literature, p-values get used as one among many tools for doing model checking, just asking if you're starting with a model that has some parameters in it, you can estimate the parameters, but at the end of the day, you have to worry, was the model good enough? Should I be thinking about alternatives? And so model checking is the kind of term of art in Bayesian inference for ways to look at how well your model predicted the data you have. And p-values are one tool that's useful for that. The Bayesian version of them averages them over the parameter uncertainty instead of just looking at the best fit parameters, which is what we usually do when we calculate a p-value. So it's called a posterior predictive p-value. But there are other tools used for model checking, doing cross-validation and some other fancier things. Basically, it involves looking at the residuals and trying to see if there's interesting structure in them. But the idea is that you should supplement the p-value with some result that speaks more directly to the probability that you would make an error in declaring whether a planet is present or not. This thing called conditional frequentist testing, which I described as just looking at the height of the histogram at the observed data instead of the tail areas, that's kind of a new thing in statistics. Not everybody is comfortable with it, but the interesting thing is that it amounts to computing a Bayes factor or an approximate Bayes factor. So it's a kind of way to try to make frequentist statistics depend more on the observed data that builds this kind of bridge between Bayesian and frequentist testing. So if you compute a Bayes factor, it has this conditional frequentist interpretation. The problem is that it depends on the prior odds. So two suggestions that are out there are just for a community to adopt what are called interim priors. I'm kind of guilty for introducing that term. I thought it was just an adjective, but it's become a term of art. where there's just some community consensus that just for the sake of reporting, we're all going to say 50% probability that systems have a planet, you know, flip of a coin maybe. And then you also have to have priors for the distributions of planet properties. Another thing to do is to report the p-value, but then also report what's the prevalence that would be needed to produce a specific false alarm probability. So like say you're interested in, you know, having false alarm probabilities at the 5% level or the 1% level, then you would say this observation could be made with I could claim a detection with a false alarm probability of 1% if the prevalence of planets was as high as 95% or as low as 1% or something like that. So that's the kind of style. No, there isn't any consensus on what to do, is the real answer, but these are the kinds of things people are suggesting. Okay.
All right, one more quick question. Did we have? Oh,
yes.
Right there.
So since you said frequency and the Bayes is different, so is there any guideline to say which one is better on the certain circumstances?
Yeah, so there isn't really. So I get very frustrated asking statisticians this question because they'll often say, well, you use whichever one, you know, performs the best. But frequentist measures of performance are different from Bayesian measures of performance. My own feeling, and a lot of Bayesian statisticians feel this way too, is that you have to struggle yourself with the conceptual distinction and decide which one of these approaches actually answers the question that you're interested in. Are you really interested in making a statement about a procedure, you know, making a statement that discusses variability of outcomes among hypothetical repeated experiments? Or are you really interested in making a statement that's harder to interpret maybe, but that's a statement about what this one experiment tells you? So for me, just the conceptual issue is, to me, it seems Bayesian calculations answer the question that's of most immediate interest. But it's still interesting how often I might be wrong if I use the Bayesian result. So to me, it's interesting to do both calculations. This is called some people call this the calibrated Bayes approach. The idea is that you adopt models, you do the Bayesian calculation, you report Bayesian results to describe what your particular data sets say. But then you also do things like p-values or even sometimes calculate a confidence region to communicate whether how often you might be wrong given your assumptions. Now you have to do twice the work, but yeah, to me the Bayesian answer is answering a question that's closer to my actual kind of intuitive question.
Okay, let's thank Tom again.